Hi everyone and welcome to Mr. Carroll's Classroom. Today we're going to look at graphing radical functions, specifically the square root and cube root functions. And these are radicals that have an index of 2 for the square root and an index of 3 for the cube root. So we're going to look at graphing their parent functions and then also transforming those functions. So let's go ahead and check it out. Okay, so in front of me now I have the graph of the parent function of a square root. It is actually right here. F of x is equal to the square root of x. And right up here in the top left of this radical, there is no number. However, typically there is a number if the index is not 2. So if there is no number, then it is implied that the index is 2, which means it's the square root. However, if there's a different number, then that means it has a different index. For example, let me go ahead and expand the cube root parent function, which is right here. And you can see that there is a 3 up here, and that is its index. The cube root has an index of 3. The fourth root has an index of 4. The 100th root has an index of 100. The reason why I'm going over the square root and the cube root only is because basically, all indices that are even are going to be very, very similar, their graphs. And all radicals with indices that are odd are going to be very similar as well. Okay? So, in other words, the fourth root should be very similar to the square root, and like the fifth root, for example, should be very similar to the cubed root. All right, so let's go ahead and take a look at these now. First of all, if we want to graph y is equal to the square root of x, we can simply just start by plugging in some numbers. And if you plug in 0 for x, well, the square root of 0 is simply 0. So that's our first point right here at 0, 0. And then let's move along, and we're going to pick nice, easy numbers, right? Numbers that I can plug in and get a whole number out. So we're going to plug in 1, x is 1, and when we do that, whoops, hang on one second. And when we do that, we get a value of 1. The square root of 1 is simply 1. And the next nice whole number here is going to be 4. So when I plug in 4 for x, and that means the square root of 4 is 2. All right, so this is essentially, these 3 points are essentially what you need to graph the parent function of y is the square root of x. Of course, you can move on after this. For example, if I scroll out, 9 would be the next likely number here because it gives you a nice whole number. The square root of 9 is 3. And actually, if I really zoom out here, you can see that the nature of the square root function is it continuously increases, but at a slower and slower rate as we move off to the right. However, there is no horizontal asymptote, so it does continue to go up and up and up as we move along the x-axis, but just at a slower and slower rate. Okay. Now, you might be asking yourself, well, what about the area to the left? Let's zoom back in here. What about all of this area to the left? Let me get this slider back over here. Okay, there we go. So if I scroll to the left, then for any x that is negative, notice we do not have any values. Now, technically that's not really true because we can actually take the square root of negative numbers. We just happen to get imaginary solutions, imaginary numbers. So while I do get a solution, that solution does not exist on this plane. This is the Cartesian plane, the xy plane, and this only consists of real numbers. However, just to give you a little preview, let's just imagine theoretically I could kind of put the complex plane and the real plane is on top of each other. Again, this is the real plane because all the x values are real numbers and the y values are real numbers. Well, let's just imagine that I can also plot the y values as imaginary numbers. So instead of 1, this is going to be 1i, and instead of 2, it'll be 2i, and this will be negative I down here, negative 2i, so on and so forth. So I'm just going to turn that on for now, and so you guys can actually see that if I was graphing on the complex plane, then you do actually get values. For example, if I plug in negative 1, x of negative 1, that means what is the square root of negative 1? Well, the square root of negative 1 is defined as I, which is just 1i. Again, we're kind of imagining here that we have this y-axis is the imaginary axis, right? And if I keep going to the left a little bit here, if I plugged in negative 4, well, what's the square root of negative 4? Well, that would be 2i. Okay, so even though this technically does not exist on this graph, I just wanted you to be aware that that piece is still out there somewhere. It just doesn't happen to be graphable on a real on the real plane. Okay. All right, so let me go ahead and take that off here. And so there you go. Okay, so now let's go ahead, and what we're going to do is we're going to compare this graph to the parent function of a cube root. So what does a cube root look like? Let's go ahead and put this back in the middle here. And the first thing I'm going to do is I'm going to actually overlay these. Let's go ahead and turn this on. So there you go. So in red, we have a cubed root. And you can see it actually, if you just look in this first quadrant, it's pretty similar to the square root, right? It goes up, it increases, and in this case, it increases a little bit slower because it's at a cubic rate. And what does that mean? Well, that means if I plug in a number, let's go ahead and trace these here real quick. If I slide this over, like if I plugged in 4, for example, well, the square root, this one in blue, the square root of 4 is what number multiplies by itself twice in order to get 4. Well, that's 2. Well, in this case, it would be, for the cube root, it would be what number multiplies by itself 3 times. So that number times itself 3 times gets you the same value of 4. So obviously that's going to be a slightly smaller number there. So it is still, it has the same shape, but it increases at a slower rate. Okay. Now the real big difference though is that you can notice that we have negative values for the cube root. Let's go ahead and turn off the square root now, and let me collapse that, and let's take a look at this this square, or I'm sorry, the cubed root parent function. So here it is. And so it looks just like this, right? And I'm using g of x here. But anyway, it's the cubed root of x, so it has an index of 3. And as I plug in values, well, what number multiplies by itself 3 times to get 0? Well, that's just 0. What about 1? Well, 1 times 1 times 1 is 1. Well, what about, oh, let me turn off, hang on one second. Got some extraneous point over here. I don't know how that got there, but that's okay. We'll just leave it there. But anyways, if I scroll all the way over here to 8, what number multiplies by itself 3 times to get 8? Well, that's 2 times 2 times 2. Okay? So we're just plotting points here, and you can actually see them down here, plugging in x and getting our y's back, our values back. Let's go ahead and scroll over. All right, and let's go to these negatives, right? So why do we have negative values for cube roots? And in fact, any index that is an odd index, you can get negative values out of it. Anything that's an even index, you cannot. You will get imaginary values once you try to plug in negative x. But anyways, so let's go over these, right? If I'm plugging in -1, that is the cube root of -1. In other words, what number multiplies by itself 3 times to get to -1? Well, that's just -1. -1 times -1 times -1 is -1. And if we scroll over to the left a little bit further, here we go. Let's plug in -8. That's the next nice whole number here that we can get out. Well, what number multiplies by itself 3 times to get to -8? Well, that would be -2. -2 times -2 times -2 is -8. So, so there you go. Those are the parent functions. Again, we'll kind of lay these on top of each other. I don't know why this point is still hanging out there, but that's okay. He can stay there. Let's go ahead and put this parent function back up. Oh, now I know why. There we go. Okay, so putting that parent function back up there and just showing that, hey, what is the big difference between these parent functions? Well, for the parent function alone for a square root, it pretty much only exists in the first quadrant here, in the positive x side. However, with any odd roots, you can actually get negatives out of it, so you do get that that negative side as well. All right, so let's go ahead and start transforming these, right? Because these are very simple. The square root of x and the cube root of x, there's really no change going on. So let's go ahead and see what it looks like to make changes. So we're going to do these one at a time. This one here is the square root of x, and this over here is going to be the transformation form of this radical. So just like all transformations, we have an a on the outside, which is going to represent a vertical stretch or compression. And also if it's a negative, then it's going to flip that that graph upside down or reflect it over the x-axis. And then we also have a k on the outside, which is going to shift this thing up and down. So let's go ahead and we'll do the outside transformations first, the a and the k. So let's do the k first. So the k literally just moves this up and down. Maybe I'll zoom out a little bit here so you guys can see this, or move it over. So the k is simply just going to move it up and down. So if I'm adding a number over here, then it's going to move all of these points up. If I'm subtracting a number, it's moving all of these points down. And well, I'll go ahead and reset that. The a on the outside, if I increase a, it's going to stretch it vertically, stretch these points up by some kind of multiplier. And if I'm multiplying by a fraction, if a is like half, for example, let's see if we can get half, right? Then it is compressing that function vertically. And if a is negative, then it flips over the x-axis. Okay, so it goes down, gets flipped vertically. Okay, there we go. So the exact same transformations that we're used to for every single parent function, by the way. Okay, so let's go to the inside. So the insides, the b and the h, are going to affect this graph horizontally. The one that you're really used to is the h, and it's x minus h. So it's always going to be the opposite because of that negative. For example, if h is negative 3, then that becomes x minus negative 3, which is really x plus 3. So if h is negative 3, it's going to look like an x plus 3 on the outside here, but it's going to be if you see x plus 3, then that means h is negative 3, which means it's going to the left 3, okay? Because it turned that negative into a positive, and vice versa, okay? Anyways, so the horizontal transformations are always the opposite. So anyways, so as h, here h is, let's say, positive 3, for example. What would that actually be? Well, that would be x minus 3, and this thing would move to the right 3. And of course, we have the opposite direction as well, if this thing moves to the right and to the left. And you can really see here that you can really take the points of your parent function and graph those first, and then go ahead and change them based on these transformations. All right, and then the last one I want to talk about, one that you may not be as familiar with, is going to be the b, which is a multiplier on the inside, which means that it's going to horizontally stretch and compress this function, and it's always the opposite. So as b gets bigger, it's going to horizontally compress. All right, horizontally compress like this. As b gets smaller, as in fractions, it's going to horizontally stretch. Okay, so let's see that in action. As I increase b, you're going to see this horizontally compress, get closer and closer and closer, these points. You can see them getting pushed in to the y there. And as b becomes a fraction, 0.7, 0.5, 0.4, 0.3, you can see it's getting stretched horizontally. These points are moving away from the y-axis. And then if it's negative, then it actually flips it over the x-axis. So you can really see, let me move this over here. So if b is negative out here, then you do have this reflection over the y-axis. Sorry if I said x-axis before. Or you could say this is like horizontally flipped. And of course, you can have all kinds of these transformations taking place at the same time. So let's go ahead and like move this thing to the right a little bit. We'll move it up a little bit. Let me put this b back at 1. Maybe the a is going to be flipped downwards. Actually, let's move this over here. So whatever, anyways. But ultimately, all these transformations are taking place on each one of these points. Okay? All right, and so let's head over to the cube root transformations. These are going to be identical because the transformations are identical for all functions. But here we go. Here's our parent function graphed right here. And so if we have a on the outside, then that is going to stretch or compress this this function. Or if it's a is negative, then it's going to flip it over the x-axis. Okay. Or you could say it is not flipped, but reflected over the x-axis. Let's see here. The b is going to, as b gets larger, it's going to horizontally compress this. And as it gets smaller, as in a fraction, it's going to horizontally stretch it. And if b is negative, then it's going to reflect over the y-axis. All right. And if you're wondering, by the way, if you're wondering that, Well, the A and the B transformations actually look very similar. It's because technically they can be kind of morphed into the same thing. Um, B is a constant, so you have to remember that. And technically, that constant can be pulled out of that cube root, which means it really is the same thing as A. If once you pull it out, once you transform it. All right, and then the last thing here we have is the H, and so of course the H is gonna slide this thing left and right, and the K is going to slide this up and down. All right, so there you go, you guys. This hopefully was a pretty basic um, introduction to how to, number one, graph the parent functions of the square root and the cube root. And as long as you really know a few of those points and you can plot those out, then you should be able to pretty easily graph any type of transformation as long as you know what those transformations stand for. Okay, all right, guys. I hope that you found this lesson helpful, and I hope to see you in the next one. Have a good one. Bye now.